Earth looks like paradise from space. Blue oceans, green continents, white clouds. But zoom in, and huge parts of our planet are surprisingly unfriendly to dense life. Water covers about 71% of Earth, yet photosynthesis in the ocean is mostly limited to the sunlit upper layer. Much of the deep sea is permanently dark. So what if Earth is not the best planet life could have? What if somewhere out there is a world with more usable land, more sunlight, and more ecosystems? Let's call our hypothetical superhabitable world Hestia. It is not a discovered planet. It is a science-based thought experiment built from ideas researchers think might favor life. Our sun has supported life for billions of years, but stars like it do not stay equally friendly forever. As the sun ages, it gradually becomes brighter. Long before the sun becomes a red giant, rising solar brightness will make Earth increasingly difficult for complex surface life. Habitability itself has an expiration date. Red dwarfs live extraordinarily long lives and are extremely common, but young red dwarfs can be violent, producing strong flares that threaten nearby planetary atmospheres. Orange K-dwarf stars sit between red dwarfs and stars like the sun, cooler, quieter, and capable of shining steadily for tens of billions of years. A longer-lived star gives evolution something incredibly valuable: time. Billions of extra years could allow ecosystems to diversify, recover, and experiment again and again. But K-dwarfs are not magically perfect. Habitability depends on the star's activity, the planet's atmosphere, orbit, and geology. A good star is only the beginning. Studies of superhabitable worlds often suggest a planet slightly larger and more massive than Earth, not a giant super-Earth, but enough to retain internal heat longer. More mass also means stronger gravity. That may help hold an atmosphere, but too much gravity could make movement, tall organisms, and eventually spaceflight more difficult. A warm interior can keep a planet geologically active for longer. That may support volcanism, crust recycling, and the long-term movement of important chemical elements. A conducting, moving interior can also help generate a magnetic field, which may reduce atmospheric erosion from the star's charged particles. A magnetic field is helpful, but it is not an invincible shield and may not be required for every habitable world. Atmospheres survive through several interacting processes. For our imagined Hestia, the goal is not perfection. It is resilience. A world that can remain wet, geologically active, and biologically productive for a very long time. On Earth, weathering, oceans, volcanism, and plate tectonics participate in a long carbon cycle that helps regulate climate over geological time. Plate tectonics may help maintain a stable climate and recycle nutrients, but scientists still debate whether Earth-style plate tectonics is absolutely necessary for life. Superhabitable world studies often explore planets a few degrees warmer than Earth because more of the surface could remain ice-free and biologically active. More warmth is not automatically better. Push temperature too far, and heat stress, ocean changes, and runaway greenhouse feedbacks can make a planet less habitable. A modest axial tilt could create seasons without extreme polar swings, producing environmental change that encourages adaptation while avoiding enormous, permanently frozen regions. Our design can also give Hestia a somewhat longer day. Rotation affects winds and circulation, although there is no single scientifically proven perfect day length. We can imagine several small moons for visual drama, but multiple moons are not a known requirement for superhabitability. Their long-term orbital effects would need careful modeling. Now we redesign the surface. Instead of one enormous dry continental interior, Hestia gets many medium and small landmasses surrounded by water. Coasts are biological crossroads where land, shallow water, sunlight, and nutrients interact. More fragmented continents could create vastly more coastline than Earth has. On Earth, distance from oceans contributes to some continental dryness. On Hestia, widespread seas and islands make enormous water-starved interiors much harder to create. Earth's ocean is deep. Below roughly 200 meters, light becomes too weak for photosynthesis, and below about a kilometer, sunlight effectively disappears. So Hestia's oceans are dominated by broad, shallow shelves rather than enormous abyssal basins, allowing sunlight to reach a much larger fraction of the seafloor. With light, warmth, and nutrients spread across huge shallow seas, reef-like ecosystems could occupy extraordinary areas, building three-dimensional habitats for countless species. But shallow oceans are not automatically perfect. Currents, nutrients, oxygen levels, and chemistry still matter. Hestia works only if those systems remain balanced. Our Hestia can have a somewhat denser atmosphere than Earth. Denser air changes heat transport, sound, and flight, but the exact safe composition would matter enormously. More oxygen could support energetic metabolisms and large active animals, but too much oxygen also increases fire risk. Biology always comes with trade-offs. In denser air, wings can generate more lift. Even with somewhat stronger gravity, Hestia could support spectacular aerial ecosystems if evolution discovers the right body plans. Some animals might become larger than comparable Earth species, but gravity, metabolism, food supply, and biomechanics still limit size. Hestia does not get fantasy monsters for free. A denser atmosphere could also change how sound propagates. Species might evolve elaborate calls, echolocation, or long-distance warning systems unlike anything on Earth. Millions of islands, shallow seas, mountain slopes, wetlands, and forests would create countless ecological niches, giving evolution many separate laboratories to experiment in. On isolated islands, populations can diverge over time. Multiply that process across an entire archipelago planet, and biodiversity could become astonishingly complex. A richer biosphere does not guarantee intelligent life. Evolution has no target, and complex intelligence is only one strategy among millions that can survive. If Hestia offers many isolated evolutionary experiments over billions of years, it is tempting to imagine more than one technological species arising independently. But this is pure speculation. A civilization born on a world overflowing with life might consider dense ecosystems ordinary and see barren planets like Mars, or even parts of Earth, as shockingly empty. A planet that is wonderful for life may not be wonderful for humans. Stronger gravity, unfamiliar chemistry, pathogens, and higher pressure could make Hestia dangerous to visit. Superhabitable means potentially favorable for abundant life, not comfortable for people. A humid, high-pressure world packed with organisms could be paradise for biology and miserable for us. And remember, Hestia itself is fictional. Scientists have proposed superhabitable criteria, but nobody has discovered a planet known to match this complete package. Researchers have identified exoplanets and candidates with some potentially favorable traits, such as greater age, modestly larger size, or K-dwarf host stars, but the data remain limited. To know whether a distant rocky planet is truly friendly to life, we need to measure its atmosphere, temperature structure, clouds, water-related signals, and possible biosignature gases. Even our best telescopes struggle to characterize small temperate worlds in detail. Future observatories will need to separate tiny planetary signals from the overwhelming light of their stars. Earth is the only living planet we know, so it is our benchmark. But nature is under no obligation to stop at the first successful design we happen to find. Somewhere in the galaxy, there may be a world where life covers almost every coast, shallow sea, and warm island. If we ever find it, Earth might suddenly look surprisingly harsh.